about her research on the upper mantle. Welcome back.
Okay. Well, thanks for inviting me. Thanks for the introduction, Annette. So yeah, I'm going to talk today about the oceanic upper mantle. My research focuses on prototypes and largely looking at abyssal prototypes. This is an example of one here. So I'm very interested in taking samples that we get of the mantle and using that to understand processes that have gone on in the mantle. And today I will talk to you a lot about the compositions of these prototypes and ways in which we are trying to use these samples that are on the seafloor that have undergone melting at the ridge but represent the convecting upper mantle, ways in which we backtrack out what processes these prototypes have undergone, what they tell us about the composition of the mantle, of that kind of great unknowable, of everything that's down there below the crust, and the ways in which rocks like these can really contribute to how we understand the upper mantle. And so this here is a sample of abyssal prototype. It may not look like those really lovely fresh xenoliths that are overflowing in Rick's office and Steve's office, but this too is prototype. So what you are seeing, the background gray stuff is olivine that is partly serpentinized. The brown stuff is the orthopyroxene. There's some bright green stuff that is clinopyroxene. There's also a distinct serpentine vein cutting through there. So these are rocks that some people would consider them metamorphic. They have undergone a later fluid-assisted alteration. But what I'm going to worry about in the talk today is what that high-temperature geochemistry tells us about the mantle. Before I go too far, I just want to acknowledge some collaborators. So 2 students, Suzanne Berner and Megan Dorico, who Suzanne's still completing her PhD at Stanford, and Megan defended successfully last year and is now at San Diego State. And then also some work that we're doing with Liz Cottrell at the Smithsonian, Fred Davis, who's now at University of Minnesota, and then also Katie Kelly. And so I will show some results from Megan's thesis, and then the rest of this group I will show in the second half of this talk our ongoing project looking at FO2 in prototypes and how we are using these samples to look at mantle oxidation state. Okay, so the first thing is that this is the general view of the mantle that I'm going to talk about today. And this is that the mantle, so we always try to come up with estimates for what mantle composition is. We know that there's variability in the composition. And the general idea that I'm going to give to you today is that the mantle is probably best represented by 3 components. So the first component I would call the depleted mantle component, which in terms of the rock and the lithology would be a lherzolite. And this has been estimated as something that has somewhere from 12 to 15% clinopyroxene. This is estimates based really on looking at mid-ocean ridge basalt and inverting their composition. There's also a proxenetic component that's down there that we estimate should be there based on subduction and return of material to the mantle. A lot of this comes also from looking at things like ocean island basalts and seeing what the isotopic composition tells us and using that to backtrack what components should be there. And then this third component, which is what I really want to focus on today, and that is refractory Harzbergite. So we often talk about the mantle in terms of this depleted mantle or depleted mantle component, and then we worry about the other end members that we see in ocean island basalts, EM1, EM2. But I think there's also a component down there that is this refractory Harzbergite, and then this is a component that's really poorly sampled by basalts. It doesn't contribute a lot to melting because it's refractory. It doesn't have a lot of stuff in it that can melt. But when we look at isotopes in prototypes in particular, and we look at other aspects of prototype compositions, there is an indication that there is this additional component down there that we need to ultimately account for when we're looking at mantle composition. And so it's this last refractory Harzbergite component that I'm going to focus on today. Okay, so the rocks that I'm looking at, these are abyssal prototypes. This map at the top is a map of the global mid-ocean ridge system in red. And in green are locations on the ridges where we have dredged samples. So this represents 30 to 40 years worth of expeditions going out on ships and dredging the seafloor. A little bit of diving, a little bit of drilling has also been done to get samples. But the bulk of what we know about mid-ocean ridge lithologies comes from running dredges from a ship. It's a pretty cheap, efficient way to get samples from the seafloor. And the samples, this is our idealized thing that we would love to be getting all the time. This is what fresh prototypes should look like. The majority of the samples that we get are these altered prototypes. So this is another abyssal peritite. One of the confusing thing about these rocks is that they have a variety of colors that they look like. They can take a while for people to get that eye in when they're working with them, because in this case, the olivine has rusted. It's been weathered on the seafloor, and so it's gone to this orange color. And then you have these remnants here of orthopyroxene and also clinopyroxene. And in thin section, right, so in this thin section, you have lots of olivine. It's the nice multicolored stuff. There's a little bit of orthopyroxene here. Here in thin section, there's a little bit of colored stuff, which is the olivine, but it's largely serpentinized. There's some orthopyroxene, and there's also a little bit of clinopyroxene. But we're always having to deal with this overprint of alteration. It also means that some of these places where I have green dots showing samples are being collected, we can't do much with the samples because what we get is sometimes 100% serpentinized. And so we're always working with a subset of the samples that retain enough of their mineralogy that we can actually do something with them analytically. So that has been one limitation sample-wise. And another thing that you'll notice in this map is that there's some ridges where we have really good coverage, particularly the Southwest Indian Ridge and the Mid-Atlantic Ridge, or the kind of central Mid-Atlantic. Other places like the East Pacific Rise over here, there's a couple dredge locations and drill locations, but largely on the East Pacific Rise, if you go there and dredge, you get basalt. It's a very fast-spreading ridge, and so it's a very hard place to sample the upper mantle or even the lower crust, because what you have being exposed to the seafloor there is basalt. And so if you go to the faster-spreading ridges, you're very limited in what you can do if you want to look at direct mantle samples. And the other reason why we have some very poor coverage, particularly in the southern oceans, is that those are the areas of the world where seas are very rough. It's very difficult to run ship operations. It also tends to be very far from the countries that are doing a lot of oceanographic expeditions, and so there's a lot of ridges where we just don't have good sampling coverage. So that's what we're working with if we want to start looking at the global composition of perittites and using them to understand mantle composition in general. As a reminder, this is what mid-ocean ridge basalt coverage looks like. So this is a figure from Allison Gale's paper in 2014. If you spend a lot of time looking at mid-ocean ridge basalt, this is an amazing compilation. It's a carefully checked database of samples, and you can see that for the ridges for basalts, we have much better coverage. So for example, and not surprisingly, the East Pacific Rise is covered in dots, indicating lots and lots of samples that have been collected and also analyzed. That in general for mid-ocean ridge basalts, we have spent there's a lot more samples that have been collected because a lot of the crust is basaltic. And that also geochemically, for data that is available in terms of major or trace element compositions, we're now up to something like 12,000 samples that are available. If we want to look at the mantle from the peritite perspective, we have about 1,000 samples that have been analyzed. So this map, this is the same mid-ocean ridge map. This is just showing now sample locations colored by the different ridges. And so these are all places where we have something in terms of geochemical data, and so we can start interrogating the geochemistry of the mantle in general using these samples. So it's definitely, compared to what we know for mid-ocean ridge basalt, this is not as extensive a data set. There are those places where we can't get samples. And the other thing is that these samples are simply harder to analyze. If you analyze mid-ocean ridge basalt, you, in most cases, getting the glossy rind on the basalt. It's a kind of pre-homogenized sample, and you can do a quick major or trace element analysis, and you need just one or two analyses, and you know its composition. If you want to look at these peritite samples, these are four-phase rocks. So you've got to collect the major element data on all four phases. You need to look at a thin section first. You have to look at it to identify the minerals. You have to measure all four phases. And these are the residues of melting. So for things like trace elements, they have much lower concentrations. And once you have lower concentrations, everything becomes harder analytically. So this is another reason why when we want to look at peritite compositions, there are many fewer samples available to analyze. But there's just less data because it's been harder to collect. It's harder to get an overall view of what a peritite composition is because it takes much more time. But I would say that now we have about 276 sites that have been that have data for them. That represents about 35 transform faults and 18 ridge segments. So transform faults have been a really great place to sample peritites. In those strike slip faults, you often have a transverse ridge and exposure of lower crust and upper mantle, whereas a lot of ridge segments, you often just have a basaltic crust. So a lot of the samples that we have come from transform faults, But there are ridge segments where spreading is slow enough that the spreading is accommodated on faults, not just on dikes and injection of magma. And on those faults, the uplift on the faults is exposing lower crust and upper mantle. And that's where we're also getting pretitite samples. And these ridge segments, in particular, the Southwest Indian Ridge and also the Gakko Ridgeway at the top, these have been really great places to look at how mantle composition is varying on the ridge segment, and also to be able to compare pritites directly to associated basalts collected from those same ridge segments. So in about the last, say, 15 years now, we've had these certain ridge segments where we have these great sample sets where we can look at pritites and basalts together, and we're really looking at the ridge processes, and we've been able to move a little bit away from the transform faults. Just a quick further comment about the sampling. Most of the samples that we're dealing with are dredge samples. There are some good drill cores into a couple places on the ridges looking at pritite, looking at upper mantle, where you have a continuous sequence and you can say something in more detail about lithologic variations, the way that you would if you went in the field and could really map in. But a lot of what we're doing is literally taking this dredge basket here, lowering it down to the seafloor, dragging it along for a kilometer, and then bringing it back up. And hopefully, when it comes back up, it is overflowing with samples, and you dump them on the deck, cut them open, and describe them. But this is nothing like going out on land and being able to really sample, knowing what you're sampling. It's a kind of hit or miss scenario where you know that you have a kilometer-long dredge track. You might have sampled systematically along that whole kilometer. You might have just hit one outcrop with the dredge basket, and everything you get comes from one little area, or everything comes for a kilometer. So we're spatially limited in that sense, in that we know that we're looking at this kilometer scale when we look at the dredge, but we cannot go from that kilometer scale, and then we can look at individual hand samples, but we can't say anything more than that those samples relate to each other within that kilometer of sampling. So this is sometimes a surprise to people that aren't used to working with seafloor samples and that have trained, with classical field geology, where you know what every sample is, and you would, if you're interested in the geochemistry, you would get a sample here and look at the veins and maybe sample away from some veins or something. In this case, this is, whatever comes up, that's what we deal with. We take the samples, cut them open, group them by the different lithologies. We often see some subset of dunites, Harzburgites, lazuli-lites, but that's all that we can really say in terms of what we sampled. It is actually one reason why we do try to, in some areas, go back in and do more detailed work with submersibles and ROVs, but it's still a much more limited way to sample than anything that you can do on land. So we have this nice, we've now been dredging the oceans for 40 plus years. We have this great set of samples that are in existing seafloor sample collections, and there's a lot of data that has been generated on these samples. So I want to look at the constraints that we have on the mantle provided by these seafloor pritites. What are these pritites telling us about the mantle? There's here at Carnegie, there's a subset of people that spend a lot of time looking at diamonds and the inclusions in diamonds, and those give you great insight into the mantle, and particularly to some really deep areas in the mantle. But we at least can say that we have much bigger samples of the mantle here. They are coming from the ridge segment, so we think that these are direct samples of the convecting upper mantle. But they have also been through that mid-ocean ridge melting process, and so we also have to strip out some of what's gone on at the ridge if we want to backtrack to what upper mantle composition looks like. So I'm going to start out with talking a little bit about the isotope data set. I'll show some of the data that I collected here and show you the constraints that the isotopes give us on mantle composition. And traditionally, isotopes have been a great way to look at the mantle, but I put up here, isotopes only get you so far. The problem in these pritites is that because they're so depleted in most of the radiogenic elements you want to look at, the isotope analyses are really difficult to do. The exception, of course, is osmium, but for everything else, it's really difficult lab work to do, and we're dealing with databases of less than 100 samples. And for that reason, I'm then going to show you what we know in terms of major and trace elements. And those data sets allow you to start looking at much larger sample suites, looking at about 1,000 samples globally, which is a better global look at the mantle, but also, as I'll show you, have some limitations. And then in the second part of the talk, I'm going to show some of the ongoing work we're doing looking at oxygen fugacity out of these global samples and trying to understand mantle fugacity. So this is just this picture again for the MORB database showing all the sample locations. And from looking at both mid-ocean ridge basalts and also ocean island basalts, we have this, this conceptual model for mantle end members. And so this is the mantle tetrahedron that some of you might be familiar with. So this is data. This is an idealized version of data plotted in radiogenic isotope space, which has been used for a long time to say that the mantle has these various end member components that are represented by the extremes in isotopic compositions that we see in things like neodymium, strontium, and lead, particularly. And that, so DMM, the depleted MORB mantle, or the depleted mantle, that's the general composition, that's the general kind of upper mantle that we expect to see at mid-ocean ridges. And then there are these other components that have been sampled at various ocean islands, EM1, EM2, high mu as well. I'm not going to worry about these components today. When we're looking at the ridge samples, we're really sampling the depleted mantle. But what I want to show you today is that when we look at the protatites, this view of what depleted mantle composition looks like is based on looking at the basalt isotopic composition. And what the protatites have told us is that that end member is probably sitting somewhere down here. That every time we analyze a set of protatites, we see things that are more unradiogenic, that are more depleted than what we have seen from the basalt data set. And it's an indication that we have a really refractory component down there that's been difficult to sample in the basalts, and that the protatites are really providing us insight into the extreme depletions that are present in the mantle. So to show you what I mean by this, this is one of the isotope systems that's used to make that mantle tetrahedron. So this is 143 neodymium, or 143, 144. And this is two data sets are plotted here. So in gray in the background is the mid-ocean ridge basalt data set. This is based on about 1,000 samples pulled out of PET-DB. So it's a subset of the samples that are in that Alice and Gale compilation, the samples that have neodymium isotope data. And they have this distribution of composition. So one thing to remember with neodymium isotopes is that enriched things sit down here and depleted things have the high numbers. So basalts have this tail going out to enriched compositions. But the really key thing that we found when looking at the protatites is that they extend to these very depleted compositions. So in neodymium compositional space, we see things going out to pretty, what would be considered pretty depleted compositions. So that's one indication that the protatites are recording more extreme depletions than we're seeing preserved in the basalts. And that's actually not too surprising if you think a little bit about processes that go on at mid-ocean ridges. So at ridges, you see mixing of melts, and the melts that you're sampling have mixed from various areas in the mantle. And anything that's depleted isotopically has a depleted trace element composition. And so it's always going to get diluted when it mixes into these various melts. And so these depleted components present in the mantle get diluted and mixed with more enriched components as you aggregate melt to erupt at a mid-ocean ridge. So it's not too surprising that we have this depleted end member. And we've seen this now looking at a bunch of isotopic systems. So this is now data for the lead isotope system, which is another system used on that mantle tetrahedron. And this is, again, the mid-ocean ridge basalt data set. There's this characteristic feature of it that it stops at the geochron. And the key thing that I want to show you is that when we start to analyze abyssal protatites, in this case looking either at clinopyroxene or sulfides in the protatites, this is data that I collected with Steve Shirey while I was here, we see a lot of samples that are similarly radiogenic to the mid-ocean ridge basalt data set, but we start to see samples that are also unradiogenic. And there's other data also from the mid-Atlantic ridge that actually extends this plot down here to even more unradiogenic compositions. And if you actually look globally at prototypes now, not just abyssal prototypes, but xenoliths as well, you see a lot of stuff that's relatively unradiogenic. So the lead isotopes are also suggesting to us that there's this very unradiogenic component in the mantle. The difficulty we have in working in the lead system in these abyssal prototypes is that it's very hard to get a lot of data from the abyssal prototypes. So in this case, there are, for the Southwest Indian Ridge clinopyroxene, there were 3 samples on here with lead data. That's actually, I ran 20 samples, and we could only extract enough lead out of 3 to actually get an isotope data set. So we have moved to this point with lead of saying it's probably we're never going to built up this really massive data set for the prototypes in terms of these ridge samples because there's so few. Connell, do you have a question? You mean these ones? Sorry, and say your question again. If yeah, so okay, so that's a good point. A lot of these samples that's showing these very unradiogenic compositions, and so the interpretation we've taken in all of those cases is that they're recording a depletion event that predates the current mid-ocean ridge melting. And that's why we like these radiogenic isotopes, is that they have such long half-lives that we're kind of able to ignore whatever the current imprint of the melting process is. And by seeing these really unradiogenic things, we would say, yeah, these samples, they underwent melting, but they underwent melting at 2 billion years in the past or even older than that. We've tried to get really coherent isochrons out of these systems by looking at multiple mineral phases, but there is some resetting that often goes on at the current ridge melting event. So it's hard to individually date any one prototype. You don't get like a pristine age preserved of a melting event, but the very unradiogenic compositions are an indication that some of those prototypes are recording past melting events. This behavior has been seen now in all of the standard radiogenic isotope systems that we look at in mantle geochemistry. So these depleted unradiogenic end members have been seen in the neodymium system, in the strontium system, in the lead system, in the hafnium system, and also in the osmium system. So this is now another compilation of global data. So in gray in the background is the basalt data set, and then in green is the prototype data set. And again, there is some very unradiogenic material that is in the mantle, indicating stuff that has been previously depleted. Another interesting thing that has been done looking at global data sets, this is from some work done by John Lasseter and colleagues, is looking at how the osmium isotopes co-vary with the whole rock aluminum content. And this is looking at an abyssal prototype data set. This is the global data set for the same osmium data set that I showed here. They took then samples that also had whole rock aluminum contents. So whole rock aluminum content is one of these parameters that's really useful in the prototype to give you an idea of how relatively fertile or refractory the prototype is. So in general, prototypes extend up to close to 4 weight percent Al2O3. So those are relatively fertile prototypes. And then stuff extends down to very, very low contents. Those are the refractory prototypes that have undergone a lot of melting. So what they're showing in this figure is that there's a correlation between the osmium isotopic composition and the whole rock aluminum composition. So it's saying that the stuff that is more unradiogenic is also more refractory in composition. So stuff that suggests it has ancient depletion also has a whole rock composition that suggests it has had a lot of melt extracted from it, and that it's and that would imply that that happened a very long time ago as well. And they actually, in their paper, they use that to calculate a model depletion age. And so this is similar to what we saw in the previous plots, that things extend to 2 billion years or a little older. If you translate your osmium ages into depletion ages, that you are getting very old ages. And so the general consensus in looking at the abyssal prototypes is that they are recording an unradiogenic component. We see that in all the isotope systems. And that to ingrow that signal, you need to have depleted the prototype a long time in its past. That can't be something going on at the ridge axis today, that you have to be removing melt some long time ago, and then those prototypes have now recirculated back to the ridge today. And that what we're seeing in at the ridge axis today are these prototypes. There's been some melting that has happened, and that melt has produced the oceanic crust. But there is also this refractory component that seems to be down there that is these Harzbergites, these very depleted samples that are possibly not really contributing a lot to the melt today. And one of the big questions going forward is how abundant are those samples? What percentage of the mantle is better represented as refractory peritite? And that if you say, well, the mantle has these refractory samples, it has a standard laserlytic depleted mantle component, and also some amount of peroxenite, it's a little bit of an under-constrained problem in that you're playing around with the relative proportions of those three things to see how you can make crust. But there is progress that can be made, and to do that, so these three components that I mentioned at the beginning, to start understanding in more detail, we have to move on from just looking at the isotope systems and looking at other things as well. So looking also at the major and trace elements. And the main reason for doing that is that we simply can't generate enough isotope data to, so the perotites in all of the histograms that I showed, those are the global databases for isotope data for these perotites. And that is less than 100 samples, right? Whereas when you look at the Mid-Ocean Ridge Basalt database, there's something like 1,000 samples if you're looking at the isotopic data, right? So there's about 10,000 samples that have been looked at geochemically, but there's always a smaller subset that have isotope data. And the problem with the perotites is we have about 100 samples. It's very difficult work to get that unless you're doing osmium isotopes. And it's unrealistic to say, oh, we're just going to, we should just send PhD student after PhD student to collect, a little incrementally more isotopic data. We have to have some other way to also look at these mantle components. And so if we go back to these 1,000 samples that have data, this is data that consists of either trace or major element data on the perotites. And they also should be telling us something about what's going on, about the mantle composition. And so the question then is, what other geochemical constraints can we get on the mantle from these perotites? So this is, again, another example of one of the residual abyssal perotites I showed earlier. And I should say that a portion of the samples that we get at mid-ocean ridges are not what we call the residual samples. So these are samples that clearly have had melt added to them. And in general, we think that's melt that gets trapped in there during melting at the ridge and inefficient melt extraction that goes on. And so there's samples like these. These are gabbro veins running through an abyssal peritite. Again, the rock type in all three of these, the main rock type is peritite. Different amounts of alteration, different styles of alteration. So these are gabbro veins in a sample, and then this is a Kleiner peroxenite vein going through this sample. So one of the things that I've done is to take all of the peritite data and in terms of looking at upper mantle composition, removed all of these melt-added samples and just worried about the samples that we would call residual and the ones that don't clearly show melt addition. So we said anything that has an obvious vein, we consider those have been heavily overprinted by the recent mid-ocean ridge process. And that leaves us with about 72% of the samples don't have any obvious veins. But I will show you in a little bit that even samples that are unveined, in often cases they have some trace element enrichments that suggest some melt was trapped behind, and that in general melt extraction is not a hugely efficient process for a lot of what we see at the perotites. That there's always some component of melt that seems to get left behind in the perotites. But to best estimate, if we want to start getting back at the upper mantle composition and looking at major and trace elements, we're taking these residual perotites that seem to be the best residues of melting without melt added and looking at their composition. And so one thing that you can do is look at the modes that we see. And so the main indicators that we want to use when we're moving away from the isotope data set and looking at the major and trace elements are things like the Kleiner-Pyroxene mode, because that's a really good indicator of the relative degree of melting. And that our estimate is that upper mantle is a lazulite represented by that star. And with increasing degree of melting, you lose Kleiner-Pyroxene and you head towards the dunite corner of this tetrahedron. And so what we see in the mid-ocean ridge data set is this mixture of lazulites and harzbergites. Places where we have really high degrees of melting, not surprisingly, so the East Pacific Rise, the fast-spreading ridge, we pretty much only see harzbergites there. And that kind of just fits with what we expect out of a mid-ocean ridge. But one of the places, or two of the places where we are not seeing things as we would expect them are Mid-Atlantic Ridge and Southwest Indian Ridge. So these are the two ridges for which we have the best data sets. And this is just plotting their mineral modes here. So Kleiner-Pyroxene, so this is basically the variation vertically is the amount of clinopyroxene variation in these samples. And the Mid-Atlantic ridge is slow spreading. The Southwest Indian ridge is ultra slow spreading. So as you go to ultra slow spreading rates, you expect less melting, because that really slow spreading, you start to conductively cool the mantle and you limit the degree of melting at those ridges. And so we would predict that when we go somewhere like the Southwest Indian ridge, we would, if the mantle is entirely this DM composition, this depleted mantle lersilytic composition, we would expect to pretty much only see lersolites there, because they shouldn't have had that much melting. But what we see is actually they cover the full spectrum in terms of clinopyroxene content. So we have a bunch of lersolites, which is what we expect, but we also have a bunch of Harzbergites, which suggests high degrees of melting, if everything started out with this composition. And similarly, the Mid-Atlantic ridge is actually, has very few lersolites. It's pretty much Harzbergitic in composition, so it suggests relatively high amounts of melting, which is, again, we wouldn't expect to see so much stuff down here like we see at the EPR, because it is a slower spreading ridge. And we can see this in other aspects of their composition. So now this is the spinel chrome number against the spinel magnesium number. So this is another one of the parameters in abyssal prototypes that we really like to look at, because as degree of melting increases, in the spinels, the aluminum goes into the melt and the chromium is left behind. And so with melting in prototypes, the spinel chrome number increases, because aluminum's going into the melt, chromium's staying behind, so you get a higher chrome number, whereas the Mg number is behaving as you would expect and is decreasing with melting. By tradition, this plot is done with this axis flipped, which is just the way abyssal prototype people like to plot this. So don't get confused by that. Okay, so again, if we were just saying, okay, if we look at the lersolites that have been collected globally, we would expect them to show a moderate range and degree of melting. But lersolites, because the cutoff between lersolite and Harzbergite is 5% clinopyroxene, we don't expect them to go to high spinel chrome number, because at that point they should have no clinopyroxene left and they would be a Harzbergite. And so that's what the lersolites do. They extend from this spinel chrome number of 10, which is around what we estimate for the depleted mantle composition, and they go up to a spinel chrome number of 30, so moderate degrees of melting. That fits with them having some amount of clinopyroxene. Things get really messy when you look at the Harzbergites, and this is now what we've seen over and over as we start to look at the Harzbergites in more detail. So you should expect that the Harzbergites would then pick up where the lersolites leave off at a chrome number of 30 and extend up to 60. And 60, a chrome number of 60 is the maximum that has been seen at any ridge. If we were looking at subduction zones, we would see things going to higher chrome numbers, even higher degrees of melting. But one of the very consistent things at the ridges is that nothing goes above a chrome number of 60. But what's very surprising is that the Harzbergites don't just go from a chrome number of 30 to a chrome number of 60. They cover this full spectrum that we've seen for the spinel chrome number, right? So these are Harzbergites that have virtually no clinopyroxene, but the spinels still look like they haven't really undergone any melting. So this is really confusing in the end, why the Harzbergites would show this much range in their compositions. And one of the things, when we've also looked at their trace element compositions, one of the things that we've concluded is going on in these samples is that they are also that some subset of these Harzbergites have been re-enriched, that they have seen some of these melts that haven't made it fully out of the mantle. So even though we've taken the sample, said there are no veins in it, this is residual prototype, all the melt was extracted, when we start looking at the prototype composition in detail, we see that there's some melt re-enrichment that goes on in the samples. And this is a little bit the complication we have in using major and trace elements to get at the mantle composition, is that there's a lot of overprinting that goes on with the modern day ridge processes. Whereas when you look at the isotopes, you see the unradiogenic isotopic composition in some of these samples. You can say, okay, those are samples that have to be, the unradiogenic isotopes have to be recording some really ancient melt depletion event. Whereas in this case, we get the Harzbergites, we want them to be these very highly melted things, but in some cases, they have they actually look relatively fertile, at least in terms sometimes of the spinel chrome number or the trace elements as well. But the other interesting aspect of this data set is the stuff that goes to really high spinel chrome numbers. So these are samples that imply a very high degree of melting. And so you could say, okay, these are just the samples, the EPR samples, which we know is a high degree of melting, those are the Harzbergites plot up there. But there are other samples that plot up there that are coming from ridges where we don't have a lot of basaltic crust. And I'm going to show you an example where we can't reconcile the Harzbergites that we're seeing with the amount of crust that you would have to generate. If you're melting stuff all the way from here to get to those spinel chrome numbers, you can do a rough calculation of how much crust can be generated and compare it to seismic estimates for crustal thickness. And the fact that those two don't reconcile, as I'm about to show you, is an indication that there must have been a refractory component that predated the melting event. So to show this point, we're going to go to the Gackle Ridge. So this is the Gackle Ridge in the Arctic Ocean. And we looked, this is work that Megan Dorico did as part of her PhD thesis. We looked at various dredges along the Gackle Ridge. So the diamonds are the prittites, and then the gray circles are the basalts. And this section here on the Gackle Ridge is predominantly Harzbergite. So these blue diamonds are Harzbergites, whereas the other ones were lherzolite samples that we looked at. So the Gackle Ridge is an ultra-slow spreading ridge. Its spreading rate is it's something like 10 millimeters per year. It's among the slowest ridges in the world, and so you really don't expect a very thick crustal thickness. What we found is that when you look at these Harzbergites, they have very depleted trace element composition. So in fact, we could find no clinopyroxenes in these samples to measure. So what I'm showing you here is the rare earth element pattern, chondrite normalized, for orthopyroxenes. So these are in situ analyses we did of the orthopyroxenes. These are really depleted compositions for these Harzbergites. So that's an indication that these have undergone these at some point in their history have had a lot of melt removed from them. We played around with a little bit of trace element modeling. Oh, actually, I should say, sorry, this is actually, we took the orthopyroxene trace elements and we calculated the bulk rock using the mineral modes. And then we ran a trace element model, just a basic non-modal fractional melting model to get at degree of melting. And we estimated that most of these Harzbergites have seen at least 16% melting or even more. And you can play around a bit with the parameters in the model to get at that. But the key is that if you say, okay, so how much crust should you produce from that melting, and does that match the seismic estimates? The answer is no. So this is the estimate for the seismic crustal thickness. This is based on data from Yokat et al. 2003. This was collected when they went up and did the dredging. They also ran some seismic lines, and they got a crust thickness, depending where they were on the ridge, that's 1 to 3 kilometers thick. That makes sense given that this is very ultra slow spreading. You don't expect, they were not expecting to find a very thick crust. The prittites, depending which set of samples we look at, estimate, so there was some lherzolites we looked at. Those have they give us 4 kilometers of crust based on their trace element contents and the degree of melting we calculate. And the Harzbergites, to get to those really depleted clinopyroxene-free samples, we estimate something like an 8-kilometer thick crust or even up to 14 kilometers. You can play around with our model a little bit, but you can't have those Harzbergites, those clinopyroxene-free Harzbergites, and also only produce 3-kilometer thickness crust. You should at least expect to find 6-kilometer thickness crust to produce, to have those very residual Harzbergites. So for us, this is one example of a place on the ridge where, without even having to look at the isotopic composition, we would say we are seeing things that this is pre-existing depletion in the mantle, and these clinopyroxene-free Harzbergites, maybe they underwent some melting now at the ridge axis, but that composition suggests that that's a pre-existing depletion that has been recycled through the mantle, so that was melting that occurred at some previous point in the history of this package of mantle, and that is now being returned to the surface. It may have undergone a little bit more melting, but it cannot have undergone, it cannot have been lherzolitic mantle that went all the way to Harzbergite, given how little crust is present there. And the other thing, just to go back to the map quickly, is that we're about to start going back in and looking at some more of these samples, because this is a pretty long segment of the ridge axis that seems to be mainly Harzbergitic, that really suggests you have a block of mantle that is upwelled here that is not capable of producing a lot of melt, that it was so depleted that it that was an inherited depletion event in that sample. So if I go back then to what we kind of expect as a function of spreading rate in the prototype compositions, so this is now a plot of the full spreading rate. So this is the range of spreading rates that we see in the oceans. And I'm going to plot the ytterbium in clinopyroxene in a second. This is the model that we expect. So if we said that if the mantle is just depleted mantle, so this DM composition, the lazuli up there, as a function of degree of melting, this is with a fractional melting model, this is the degree of melting that we expect to see in the prototypes as a function of spreading rate. And that's really just saying that in general, we expect the same degree of melting until spreading rate gets so slow that conductive cooling limits the amount of melting that occurs at the ridges. But what we see in the data set is this huge range in compositions at very low spreading rates. So the East Pacific rise has these very depleted compositions, and that agrees approximately with what we expect based on high degrees of melting at fast ridges. But when we go to these lower spreading rates, we see a huge range in their compositions, which is that same range that I was showing for things like the spinel chrome number. And that's suggesting actually, so some stuff is enriched. That gets back to this idea that melt extraction is not always an efficient process. It also agrees with some of the enrichments we've seen in the isotopes, which suggest there are some enriched components in the mantle that we're recovering. And then we see some things that get to really depleted compositions. And we see it as well if we look at the spinel chrome number. We see a whole bunch of stuff that has this high spinel chrome number, but we wouldn't expect to have that high degree of melting. And in places like the Gackle Ridge, where we can really join up the observations we have to things like seismic estimates of crustal thickness, we can really say, okay, just based on the major and trace element composition of these samples, we must have an inherited depletion that's present. And so we're seeing, again, this evidence for this very refractory component in the mantle. Okay, so I want to just say, well, where do we go with that? And one of the things that we're starting to do is to look at the oxygen fugacity in these samples. So one thing about having this is that we now, okay, this is what we know about composition of prototypes from ridges globally. There is this huge gap is something that might get a little bit filled in. There's some places on the ridges that match these spreading rates, and you might, if you go to the transform folds, be able to get prototypes, but we aren't. This gap is just something we have to accept to some extent as being a limitation of the samples that we have. But we can now say, okay, if I want to understand the high spinel chrome number samples in more detail, then we can say, okay, well, so maybe those are the samples we should really be looking at for isotopic analysis, rather than just kind of looking at a suite of samples for the isotopic composition. If we want to get at that refractory component that's in the mantle, we should really be looking at this stuff that's high spinel chrome number, no clinopyroxene, to understand that in more detail. And to have much more focused sampling, so to be using what we know about these compositions now to explore specific components in more detail. Another thing that we've started doing is going back to questions about oxygen fugacity in the mantle, and looking at that in more detail. So I'm just going to use the last 5 minutes to just show you some of the preliminary results we have from revisiting this question of oxygen fugacity. And this is motivated by a bunch of observations. So in recent years, as some of you I'm sure are aware, there's been a lot of interest in doing zanes on basalts and using that to look at the FO2 of the mantle. And so this is a data set from Kelly and Cottrell, or Cottrell and Kelly in 2011, looking at 100 basalts, and they get a pretty systematic estimate for mantle FO2. And prototypes have not really been looked at since the early 1990s, when this spinel oxybarometry method was developed. And a bunch of samples were analyzed, and they said, okay, this is the average FO2 of the ridge. There were a couple more studies done on that, and then people kind of have moved on from doing that. But we decided to revisit this partly to understand why this offset might exist, but also because when we started looking in detail at what those 30 samples are, they are not a representative global sampling. So they come from about 3 or 4 locations on the Southwest Indian Ridge and on the Mid-Atlantic Ridge. And if you want to say this is globally what abyssal prototypes look like for FO2, this is not a representative sample set. And one key question is, if you start to ask why is there an offset between these two things, we're not looking at prototypes and basalts from the same location. And so the first thing we said is that if we want to understand this, we need to at least look at samples from the same location to rule that out as an issue. And so we are fortunate in that to do that, we're now going to this section of the ridge called the oblique segment. It is in the southern Atlantic Ocean on the southwest Indian Ridge. And it is one of the other sections, like the Gackle, that is ultra-slow spreading and has had both protatites and basalt sampled from it. And so we can look at both types of samples to look at that FO2 value. So this is just a summary of the dredges that were done along the ridge axis of both protatites and basalt. So this is one of about 3 or 4 places in the oceans where we have really good overlapping sets at the regional scale of both basalt and prototite. We also spent a lot of time on the spinel oxybarometry method. So this is the Bernie Wood method where you are measuring the 3+ to total ratio in the spinels and then using that to calculate an FO2. And there's actually a paper out by Fred Davis in the February issue of American Mineralogist that goes into the methodology in detail. And one of the things that resulted us doing is we recalculated the literature data and everything shifts up a little bit because of various inconsistencies that we identified in how the conversion had been done from the 3+ to total to the FO2. So that is narrowed a bit, but that doesn't get at the overall issue that this global data set is not truly a global data set, and that we're looking at things from different locations. So this is the global prototite range, and for the southwest Indian Ridge, this is what we found. So these are the prototite data set, and we looked at a bunch of different dredges. In some cases, in most cases, we analyzed multiple samples from each dredge, and we found considerable heterogeneity among the samples. And so this was somewhat unexpected, but maybe not surprising, given that we often, within individual dredges, see a lot of compositional variations going on. And we're still trying to understand how all of this scatter relates. You can also see this is the average of the samples that we looked at. This is the global average. We're looking in our data set at about the same number of samples that go into that global average. So I would say one straight out thing is that I don't think we have a good global average at the moment because I don't think we've analyzed enough samples, and that we really need to go back and look at more samples globally and use what we know about major and trace element compositions to guide that sample selection. We also have done some Zane's work on the basalts to start making a comparison between the two. And so this is the basalts from the same section of the ridge axis compared to the prototites. At the moment, it's suggesting that they both are slightly more oxidized than the ridge axis, but that's not necessarily an offset between the two. There's still some issues with how we calculate FO2 from the 3+ to total for both basalt and prototite, so I wouldn't say that's a definitive result. But then there is one final surprising thing that we found, which is that there's a subset of samples that are very reduced, and these are our really high chrome number samples. And these are these clinopyroxene-free Harzbergites that we looked at the Gackle Ridge. Actually, sorry, these are the southwest Indian Ridge samples that the subset of high chrome number clinopyroxene-free Harzbergites. And it turns out for the Gackle Ridge that things get even more reduced. And this was kind of surprising. We're not really expecting to see that the FO2 was, that the mantle oxygen fugacity recorded in these samples should be following degree of melting. But at the moment, for the samples that we've looked at that are these high chrome number clinopyroxene-free samples, they seem to be coming out as also very reduced. We're at the very preliminary stage with this of trying to understand what that is really telling us. But one thing for sure is that we should also be going back to the samples and looking for these other very highly melted samples to see what they're telling us about this component that seems to be down there in the mantle that is very refractory in composition, to start exploring that more in terms of other geochemical parameter space. So I will leave things with a picture of one of the freshest prototypes from the seafloor. This is actually from the Tonga Trench, and it's pretty much a pristine sample, which is its own separate story, but it is a very beautiful sample. So thank you very much. So what was the site? Change the composition of? Not necessarily, because there's also this proxenetic material that's down there, and so it could be that it might be that if you say, like, the more Hausbergitic material you say that, it could be that to kind of produce your crust or something, you just then basically saying there's some larger amount of proxenite there. So at the moment, if you look at the number, kind of the percentage of refractory prototypes in the database, it's like about a quarter of them if you go on the bulk rock compositions. So maybe 20 to 25%. And then the current estimate for the amount of proxenite in the mantle is something like 5 to 6% because 5 to 10% because it disproportionately contributes to the melting at ridges. But it really depends on how you tweak those two as to how much that's going to influence the bulk composition. But we're also in an under-constrained problem, so if you, I don't know that we can independently come up with a bulk earth estimate, but if we can come up with a concrete estimate of the amount of refractory material down there, you then would want to forward propagate it into these models for crustal production. Yeah. Yeah. Those ones, we think, these ones at the top that are relatively high spinel chrome number. So we've really just been going through this data set in detail for the last couple of months. And these samples, we've gone back to them petrographically, and we think at least some of them have evidence of plagioclase, which would indicate melt and re-enrichment. So that's one of the difficulties with these Hausbergites, is that their compositions are so refractory that a little bit of melt around there is going to really tweak their compositions. Yeah. So the unradiogenic osmium, one explanation that's been given anytime unradiogenic osmium has been found in the abyssal prototypes is that is recycled subcontinental lithospheric mantle. But I think that we see that stuff too ubiquitously, not just at Gackle, which is relatively near continents, but somewhere like Southwest Indian Ridge or Mid-Atlantic Ridge, where you're so far from the continents that either you argue you always entrain subcontinental lithospheric mantle back into the ridge system, or you say that the unradiogenic component is not necessarily SCLM, but it is a ubiquitous refractory component that is present in the upper mantle. And so I think that we see it too often to every time we see a refractory Hausbergite or this unradiogenic osmium to run around saying that has to be SCLM. We see it at too many ridges to do that. Well, the modal data gets people very upset because first of all, it's a lot of work. It takes 4 hours to point count one thin section. But some people will say, oh, there's too much analytical error in this because you're sitting there point counting partly serpentinized samples. And there is scatter in this. And the orthopyroxene enrichment that they're talking about is kind of this scatter that you see at the Mid-Atlantic Ridge. Definitely there's a 5% error at least in some of these point counts, but I don't think, this to this is wrong. And so there is various orthopyroxene enrichment that you see. But to me, that is an inherent part of these abyssal prototypes. and their evolution with melting, and not every time you see something with high orthopyroxene is not an indication of SDLM. So I think it's multiple events. That potentially what you're seeing is you're recording, various episodes of melting at mid-ocean ridges, and then that's lithosphere that eventually gets recycled back into the mantle and comes back to a ridge system. The histograms that have been done with isotopes where you can get at an age often give you about 2 billion years. So you see that in the lead, you see that in the osmium. But I think that is not telling you that there's some major event at 2 billion years, but that is an average of the mixing that has gone on, and that is why you're seeing that. And I think we've also undersampled the system. That the system is undersampled as well. That I don't, for the prototypes, I don't think we have enough data, particularly for things like lead, to really say. I don't think so. I mean, Steve and I said this in our paper in 2012, that that's kind of an average mixing age for the Earth. If the Earth is 4 billion years, that's just the average out of everything that's being recycled back in and gone back around. Mm-hmm. Yeah. Yeah, I mean, I would say the main limiting factor is that the lead abundance in these rocks is really low. And so for the clinopyroxene, if you want to do lead on the clinopyroxene, they have about 10 ppb. And so you have to use really large mineral separate, which has its own problems. And the sulfides have an average concentration of 2 ppm, which is also really low for getting the isotope data. And so it's simply being an analytical problem to be able to produce enough data to be able to really, I would love to have lead isotope data on every one of these prototypes. Yeah. Yeah. I guess I would just prefer to have more data on some of these samples to do that off of, because at the moment we have, it's like 5 samples of Southwest Indian Ridge, 4 from Mid-Atlantic, and like we don't have a lot, and I don't know that we've seen, say, the most unradiogenic one to do that. So the prototypes that we're looking at, you can estimate the approximate age to say when they were 1200 degrees C, so when they were in the convecting upper mantle. But everything, the ridge samples are collected relatively near the ridge axis, so they're all kind of 0 to 15 million years in age. So that's the recent age if you look at how closely they're related to in the current melting event.
But if you want to look at the averaging and recycling
yeah.
property, maybe how it compares with like
Oh, if you look at, say, the osmium histogram compared to, um, yeah, so there are some studies where people have taken often the osmium data set because it's the most abundant and looked at histograms for, say, a bunch of ophiolitic prototypes and also the abyssal prototypes and compared them. And they often come up, well, the statistics in those papers aren't great, I should say. So there's a subsequent paper that argues that they didn't sample the system enough. But you can see some peaks going back in time. And the abyssal prototypes is 2 billion years that it seems to give, but I don't, I still think we're undersampling the system, and you probably have to do a more sophisticated statistical treatment to look at those peaks. With the subduction zone systems, you have a better chance of, say, relating it to, so like orogenic prototypes that have been abducted with, associated with a subduction event, you often would have a better chance than of associating it with ages that relate to some of that system.
I'm curious about in the last figure of the oxygen to gas phase. I don't know really how the oxybarometers work, but I was curious if it's possible that really reduce looking samples that could just be an effect of the high degree of melting, pulling out all of the ferric iron, so you're left with basically no ferric iron.
Yeah, but why? But we wouldn't necessarily expect the melting to be pulling out all the ferric iron. So this is determined. This is derived from the 3+ to total ratio in the spinel. So
Ferric iron is a fairly incompatible.
yeah.
So higher degrees melting would pull out the ferric iron preferentially and leave you with a residue that looks reduced because all of this 3+ iron is gone out into the melt.
Yeah. Yeah, and but you're also, I mean, the olivine. Yes, but the oxybarometer is also taking into account the olivine and orthopyroxene composition, so that should, I think, even that out to some extent. This is one of the things that I've not thought in enough detail about yet, as to whether this is simply reflecting the melting process or whether it is an inherited signature that is independent of the melting. And we haven't tried to model anything yet to see how the 3+ to total should be behaving with the melting. Yeah.
That the ferric iron ratios, analysis looks like basalt is more uniform.
Yeah. So, yeah. So I mean, the initial interpretation for that is simply that the basalts mix melts from large areas of the ridge. And in fact, for this section of the Southwest Indian Ridge, there's some 3D models that have been done looking at how melt is localized to specific volcanic centers along that ridge. So the greater heterogeneity in the prototypes, you could say, well, any individual basalt is still a mixture of melt from a large area, and so that you're averaging out some of that variability in the prototypes in the process of generating a mid-ocean ridge basalt.
It also could reflect more complex history of
Yeah. Yeah.
And one thing that comes to me maybe was interesting to read is like taking some of those experiments really representative projects and probably taking those samples really further as this oxygen to gas system to get
So Liz Cottrell and Fred Davis are doing some experiments, not on this, but just synthetic to just equilibrate the melt with prototype, just to see if you get the same result from the melt and the prototype. But you were basically saying to go to the next step and see if those are actually in equilibrium. Yeah. 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 But these, yeah, I don't think you can actually do it on those samples. You could, like, because that's serpentinized as well. So, yeah.
So you can separate enough of this, the purchasing and.
To do a mineral
separate.